today's lecture will be on the normal distribution. We will motivate it by introducing it as an approximation to the binomial. So just before this, let me just motivate the normal distribution. So there are many continuous distributions that we will see. So among all continuous distributions, the normal is kind of the most fundamental in terms of applications. So the normal distribution is the most fundamental in terms of applications. It frequently arises in many situations. So let me just write down a few. So it frequently arises as a limiting procedure or a limiting distribution of sampling procedures. So it has a particular density, and it's a random variable density. But what we will do is we will try to sort of motivate it from the binomial. But before that, some more examples I'll give you. So one is as a limiting distribution of sampling procedures. The other is in real life. If you go and check, for example, the number of leaves in a tree in let's say in a people tree, let's say. That's supposed to be the normal distribution, let's say height of adult men in a population. If you tabulate it, it's supposed to follow a normal distribution and with certain parameters, which you'll come to in a certain sense. So these are examples where how the normal appears naturally. Just erase a little bit. Yes. So now I wanted to motivate it as an approximation to the normal binomial. So let's see. So let me try and start that process. So let x1, x2, xn be IID Bernoulli p random variables. So these are, so xi's are take 0 or 1 with probability x. So let's say xi takes value 1 with probability p, value 0 with probability 1 minus p, and they are all independent. So that is for all I bigger than equal to 1, xi takes. Very good. So now, what we did how did we construct the binomial? The binomial we would take Sn to be the number of successes in n trials, or if you think of xi being 1 as success, this I equal to 1 to n xi. Right? That's binomial, and this we know is like a binomial NP. So how do we know this? This we say that, we know that the chance that Sn equal to k is given by n choose k, p power k, 1 minus p to the power n minus k for k in 0 to 1. Very good. So now this we have already encountered this distribution before in the discrete setting. Okay, let me move to the next page. So one approximation we already seen. So let's say one approximation. So let me call this approximation 1. So an approximation already seen is the following. Let's see, approximation. This is what we have seen is the Poisson one, which we've already seen. So let's recall this. Right. So let me erase it again. Let me see if I can draw a straight line. So here, what did we know? We know that if p was like lambda by n, where lambda is a fixed quantity between 0 and 1, let's say, and we observed the chance that what happened to Sn equal to k, which was again n choose k, p power k. P power k was now again I'll write as a lambda by n, the whole to the power k, and 1 minus lambda by n, the whole to the power n minus k. We knew that this converged as n goes to infinity for each fixed k to e to the minus lambda, lambda power k by k factorial. Right? So this is for all k bigger than or equal to 1. And note that as n gets larger and larger, this p is changing. So this is in fact like a p sub n in some sense. Right? And this gave us this idea that this new distribution, a genuine one on the natural numbers. So we called it as the Poisson lambda distribution. So we said x follows lambda if range of x is 0, 1, 2, 3, and so on and so forth, and the chance that x equal to k was e to the minus lambda, lambda power k by k factorial for all k in the range of x. And you were able to verify that this was a genuine distribution and so on and so forth. Very nice. Very good. So now what I want to do is I want to do a little different approximation. So here if you notice, let's make some notes. So some notes. Right. So one is that p sub n sort of converges to 0 as n goes to infinity. Right. Right. So the probability that go into 0 as n goes to infinity. And but also notice that the n times Pn is always going to be lambda, and this remains constant. These are two aspects of this convergence that you should keep in mind. So now the question I want to understand is that what happens when P is fixed? What happens when P is fixed and n goes to infinity? Very nice. So that's the question I want to understand today. Let me go down. So that is what our next topic will be, or the topic of this lecture will be. It's called the Demovies and Laplace central limit theorem. So it's called the Demovies. So I hope I'm pronouncing it correctly. So the spelling is wrong. Central limit theorem. So this is a special central limit theorem. There's a sort of a much more general one that's available, which we will not do in this course, but in the next course in probability 2. But this particular aspect is only apply for the binomial case, and which we'll discuss today in this class. Okay. So what is the theorem? So this is theorem 5.2.10 in the book. So what's the theorem? The theorem is, let's say I'll write again, Demovies Laplace central limit theorem. So what does it say? Let's write down. So let's say it says the following. Suppose Sn, so Sn has to be binomial. Sn is binomial of n comma p. Okay. Sorry, p is fixed now. 0 less than p less than 1. It's fixed. Then the remarkable thing is, for any a less than b, real numbers, you look at the chance that your binomial lies between its scaled mean, standardize it, divide by, you center it and standardize it by standard deviation. Okay. You standardize a random variable. So that's less than equal to b. This converges as n goes to infinity to an integral of the form a to b e to the minus x squared by 2 over root 2 pi dx. So it's a very powerful result. So it tells you that the probabilities with which the Sn minus Np divided by the square root standard deviation is between a and b converges to the integral a to b of this function. What's the consequence is that this in fact is a density, and which is what I'll write down. So a consequence of this is that we'll show the theorem in a second or give a sketch of the proof. The consequence is that this is in fact a density. So this is a like definition. Let's say in the book it's 5.2.9. So here I say that x is said to be normal with parameters mu and sigma squared, where mu is in R and sigma is a positive number. If x has a PDF, a probability density function, given by f of x is equal to 1 over square root 2 pi sigma e to the minus of x minus mu the whole squared by 2 sigma squared for all x in R. So this is what the density will look like. So one can actually check this. I will not do in this course, but one can actually check that f is indeed a PDF. That is, one is f is continuous, f is non-negative, and the integral from is equal to 1. This is the hardest part, but the other two are kind of standard, but this requires some work, but these are all facts that are true. So what we have shown is that the binomial as n gets larger and larger, if p is fixed, the standardized one will converge to the normal distribution. Okay. That's the theorem that I would like to sort of give you a sketch today of the proof, and then we'll come back and discuss sometime later how to work with the normal distribution. So the way one does it is in a sort of a very analytic way, so it can be confusing. So, but let's see. Let me try and walk you through the main steps. The details are quite hard to do. So let's go to the next theorem. Okay, or next page. Sorry. So let's go to the proof of the theorem. So proof of theorem 5.2110. Right. So here, what you have to do, you see what are our events of interest. Our events of interest is the form that, so in the proof you have to understand how do these events behave, right? So these events Sn, sorry, let me write down here a little bit. So event was Sn minus Np divided by square root of Np times 1 minus p is between A and B, right? Okay. So this I will write it like I'll call this event as A sub n, just for us. So what is this? This is just so set of all k such that k is between 0 and n, because Sn takes values only between 0 and n, right? Such that what happens, I'll rewrite this expression a little differently. I'll think of it as A times square root Np times 1 minus p, the square root, right? Then plus Np is less than equal to k is less than equal to b times square root Np times 1 minus p plus Np. So I've just rewritten the event, in terms of k, which I can handle properly, right? So that's, I'll think of An as this, and Sn is equal to k. So k is between 0 and n. K is and this expression holds that A times square root Np plus Np is less than equal to k, and Sn is equal to k. So what we could do is we could rewrite the chance of An, the probability of An, as the sum over k in An such that probability Sn is equal to k. That's just the same thing, because each k in An can occur. If one k in An occurs, the other k cannot occur. It's a probability expression right here. So sum of mutually exclusive events, so probability sums up. Right? So then our analysis turns out to understanding, what do we want, what's the objective? Our objective is to understand the limit as n tends to infinity, the probability of An. Right? That's our understanding. Right? Very good. So what we'll have to do is we'll have to decompose the probability Sn equal to k. Right? So how do we decompose that? So now let's go back to the proof. So the in blue, for example. So the probability Sn equal to k is going to be what? Is going to be n choose k p power k 1 minus p to the power n minus k. So this I will split up nicely. So I will do nicely. So first step is, so this is what this is given to us, 0 less than k less than equal to n. This is true. So there are 4 key steps. So I will not do the exact proof. So the whole thing is to analyze probability of An carefully. So I will give you the sketch of the proof in a sort of very, very precise way. So here are the steps. So what we'll do is a sketch of the proof. So I'll give you a sketch. So it's not a complete proof, but it'll give you the key steps, and you'll be able to do the proof by yourself later. You work on it slowly. Okay. So what is step 1? Step 1 is the following. So what you have to do is you have to use something called Stirling's approximation. So maybe I'll write that in blue itself. So Stirling approximation. It's called Stirling's approximation. So what happens here? In this, you have to show that you have to show sort of uniformity. You have to use it to show uniformity in some sense. You have to show that you look at everybody in. Let me erase this and write it in black. You look at everybody in Kn. You take the larger of them. So it takes, right. You look at. Let me write it as max. No problem. So the maximum of them. Everything Kn. So it's finitely many. You can find the maximum. You look at n choose k. This is the probability p power k. 1 minus p to the power n minus k. That's what the expression probability Sn equal to k is. So you look at everybody, and you show this is of this order that I'll write down. Write down as e to the minus xi kn squared by 2 into square root of 2 pi times p times 1 minus p times n. So you look at the bottom function and you show the top function in terms of n and p is like the bottom function, and this converges to 1. Okay. Of course, I have not told you what xi kn is. So where, let me write down where, maybe I'll go to the next page and write down xi kn, where xi kn is just what you expect. It's just k minus np divided by square root of n times p times 1 minus p. So let me just cut and paste this thing. Let's see if I can do that properly. Oh, sorry. Let's put it down. Let me go back and write. Sorry. So that's the first step you have to do. You have to establish this thing that the order of the top term, that the order of this top term is like exactly like the bottom guy. Okay. So once you have this, here is step 2. This step 2 is something that you may have seen in your calculus classes. It's not so hard to try. But again, this is a little bit tricky because you need to know exactly how to do Riemann approximations. So what you do is you show that the limit as n tends to infinity, the sum over k in a n, right, e to the minus xi k n squared by 2, that's the bottom term, I'm writing the bottom term, divided by, so I think I may have made a mistake here. So here I should put to the minus 1. So this divided by root 2 pi p into 1 minus p times n, this converges to what we want, ab e to the minus x squared by 2 over root 2 pi x. So this is the second thing. So once you show these two steps, you're almost done, because then all you have to do is in step 3, just have to observe the following fact. This again is a little bit hard step to do, but if you just keep your head straight and the hand steady, this should be work out. That is the chance that a less than Sn minus Np divided by square root of Np times 1 minus Np less than b, less than equal to b, is equal to, you write it appropriately to handle the top terms, right? So you first write it as what you like, that is the sum over k in a n e to the minus xi k n squared by 2 by root 2 pi p times 1 minus p times n. So this is exactly the term that matches your step 2, right? So exactly that matches the term step. So this part is going to go to your integral, right? So step 2. So we are right below, so it's clear. So this is the part that matches step 2. Right. Then what's left is you have to show the left is an error term. So what you do is you just add. What's the error term going to look like? You're going to have this guy minus what the actual probability is, right? So that I will write it a little bit cleverly. So I'll write it as like summation k in n. So it's going to be this minus the probability Sn equal to k, right? That's what it's going to be. minus the probability Sn equal to k, right, which is this term. But I'll write it a little jugglery. So what I'll write as e to the minus xi k n squared by 2 divided by square root of 2 pi p 1 minus p to the n, and then I'll put a big bracket in which I'll put the two terms in. So I'll have probability Sn equal to k, that is n choose k 1 minus p to the power n minus k. Or I'll write as just do it in two steps. So I'll write as probability Sn equal to k divided by this person, right? So divided by, so let me copy this. Let me see if I can copy this properly. Let me copy it, copy, and let me go here, and let me paste it. See if I can paste it. Very nice, I can paste it here. I'll make it a little smaller. Okay, very good. Then I go here and I say this minus 1, right? That's the exact expression for this guy, right? There's no problem, right? So let me just be a little bit more careful for you. So this is same. So let me go here. Let me just move this across. This is the same as like we discussed before. So I go here. The sum over k in an probability Sn equal to k, which is equal to this, which is equal to this plus this, right? So now all I'm doing is, I know one looks like step 2. All I'll have to just point out to you that the third guy looks like, the last guy looks like step 1. Okay. Right. So maybe I'll just move this down so it's all clear in the notes at least. Very good. I know what's going on. Let's see. Okay. Let me erase and write again. So no problem. Put my text here. Erase this guy. Equal to this guy. Let me try one last time moving this around. Let's see if it works. Right. Very good. So now all I have to do is just make sure that I keep track of everything that's going. This is like step 2, like we discussed. There's no problem. Like this is no problem. And this guy is the same as the previous guy, but except that now, if I want to compare it with step 1, all I have to do is just identify the top term, right? So paste it here. So we go to the eraser, we erase this part. This part, I'll erase it. I'll write it as n choose k p power k 1 minus p to the power n minus k. Very good. Now if you just scroll back up and just look at what step 1 did was exactly that, right? It just had this exact Stirling approximation term that we have here, right? That's exactly right. The same as the top one. So now just come down here and you observe that this person right here mirrors step 1. So matches in blue step 1. So once you do step 1 and step 2, and then the proof is kind of complete. So this will converge to the integral from a to b e to the minus x squared by 2 over root 2 pi dx as n goes to infinity by step 2, and this will go to 0 by step 2. Very good. So that's the sketch of the proof that will give you this the result let me go back to the statement theorem that the probabilities of the binomial when you are centered and standardized by the variance by standard deviation will converge to this integral. Right? And this integral is just the normal distribution with parameters mu and sigma squared. So let me write that down. So this integral here is the chance that let me write a normal 0, 1 is between a and b. So this is like sort of a very important result. That is, if you want to compute the binomial probabilities for large n, but when p is fixed, then this is one approximation one can use. That one uses the fact that the chance that the binomial, when you center it and standardize it by the standard deviation, this converges to the normal distribution with mean 0 and variance 1, because with parameters 0 and 1, this will come to be clear later on in the next course, that is mean and variance, but not in this class. So this is one motivation for considering the normal density. So there are also, like in the Poisson case, some extra notes. I'll conclude with that for today. Some extra notes or remarks is that so one thing is that we also know that if you have PNs which look like lambda by n's, that is PNs are going to go 0 with NP being a constant lambda, then one can use the Poisson approximation. Then the next thing is to understand is that when P is fixed and n goes to infinity, this is Pn as n goes to infinity, Pn goes 0, and P is lambda, use Poisson approximation. P is fixed, n goes to infinity, then one uses the normal approximation. So here is it. Again, there is a small caveat here. So one thing to think about is, when is this good? So when is this good? Right. So this is something one can check, which I will not show in this class. If P is close to half, then it's very good. Very good to use. Otherwise, you may have to take n very large. If P is not near half, otherwise take n very large. You have to take n very large for the approximation to be good. So for in terms of applications, you need to take n very large for the approximation to be good. So that's one thing we will should keep in mind for approximation, and this is the motivation for considering the normal distribution. So in the next class or so, we will try to come and understand how to work with this density. It also requires a lot of work, because ultimately you want to use this to compute these probabilities, right? So that will take some time. So we'll do that next class. Thank you.